Hello everyone, this is Solar Tiger, and today I'm going to start on a project where I'm going to give you an in-depth tour of my solar power system. So I'm starting outside in the garden, as you can see, and I'm going to show you the solar panels. If I just pan round, these are my solar panels. These are monocrystalline solar panels. There are three types of solar panels available on the market today. There are monocrystalline panels, like these ones. These are the most efficient, but the most expensive. For a fixed wattage, you will need the smallest number of panels to produce this. Polycrystalline panels, or also known as multicrystalline panels, are the next lowest of efficiency, but they are cheaper, so they are a trade-off, a worthwhile trade-off. And the third type are amorphous panels. These are the least efficient but the cheapest, and are usually used for small solar panels, i.e. to power outside garden lights and water features, mainly because of their low efficiency. To get any worthwhile power, you would need a large number and a large surface area of panels. So these are my panels. They are screwed to the roof with these brackets. I'm sorry for the knock there against the ladder. These are the brackets that hold the panels in place. Use of these brackets is important because they raise the solar panel off the surface, as when they are in bright sunshine, the solar panels do get warm, and the warmer the panels get, their efficiency goes down, so we need a gap under the panels to provide air to flow underneath to help cool the panels. So these are my panels. These are 100 watt monocrystalline panels. These are what is known as battery panels because they have a maximum power voltage of 17.2 volts, which means they are suitable for battery charging. They have an open circuit voltage of in excess of 20 volts. That is with an open circuit. The panels are wired with 4mm cable. These cables came pre-fitted to the solar panels and were terminated with MC4 connectors. These are the industry standard for solar panels. They simply click together to make a connection and are waterproof for outdoor use. These panels were bought from eBay for a cost of approximately £80 to £90. Each solar panel is made of individual solar cells. I'll show you here. Each square that you can see is a solar cell. Each solar cell in bright sunshine produces 0.45 to 0.5 volts, which on their own is not a lot. So the cells are wired in series to create a solar panel. Since these are the so-called 12 volt panels, they contain 36 cells wired in series to produce the open circuit voltage. These two panels are wired in series to produce a nominal 24 volts, although in everyday use the voltage can exceed 40 volts, so the output can go into the low 40s volts, so that's something to bear in mind. These panels are wired in series since I'm using an MPPT charge controller, although if you're using a PWM controller you will wire your panels in parallel, but more about that later. The output from the panels is fed into my feed cable, which is 4mm squared solar PV cable, and this feeds all the way along and into the house. I will take you inside in a moment to carry on to the next section of my video. I will see you all in a moment. Okay everybody, I am inside. Just another point to mention when installing your solar panels: the best location for your panels is a position that faces due south, where your panels will get the maximum exposure to the sunshine, and the angle which you fixed your panels should equal the latitude of your location. So that is that. The next part of my video is about charge controllers. There are two types of charge controllers: PWM controllers and MPPT charge controllers. The PWM stands for pulse width modulation, which is a method of controlling the charge going into your batteries. A PWM controller turns the connection between the panel and the battery on and off many times per second. The ratio of the on time to the off time decreases as the battery reaches a full charge. When the battery reaches the full charge voltage of the controller, it switches to a maintenance or float charge, which just maintains the charge on the battery without overcharging it. The MPPT stands for maximum power point tracking and is a more efficient method of charging batteries from solar panels. The MPPT charge controller can take a high voltage from the solar panels, i.e. if you connect several panels in series. The advantage is that the high voltage can be converted to a low voltage at the other end of your feed cable, and which means that you transmit a smaller current down your feed cable, which leads to less wire losses due to resistance in the cable. The controller converts the high voltage down to the correct voltage to charge your batteries, usually between 13 and 14 volts, but increases the current so that your batteries charge faster and you can power your load devices more efficiently. I will show you a couple of controllers and tell you the pros and cons of them. Sorry about my finger there. So I shall take you to my workbench and I will explain more. Here we have two charge controllers. I will show you a few more as well. The controller on the left is a PWM controller. This is a Sunsei. It is a fairly basic model. There are 4 terminals on the controller, 2 for the solar panel input and 2 for the battery input. There are 3 indicator lights, as you can see here. The bottom LED would normally be red, and this comes on if your battery gets very low, which it may be due to you using your loads for a prolonged period, or there not being much sun, or if the connection between the solar panel and the battery became disconnected without you knowing, then your battery would run down and this light would warn you of that. If you get to the point where this light comes on, you must stop using your loads immediately and charge your batteries, either by remedying the problem by connecting your solar panels or by using a mains powered battery charger. Batteries must never be left in a discharged condition for any period of time, as this will damage them. The LED in the centre comes on when the battery is nearly fully charged but has plenty of charge in it. The light on the top comes on when the battery is fully charged, and with this particular controller, when the controller is in a maintenance charge, the light is flashing. So that is the PWM controller. This particular controller can handle a current of 25 amps from the solar panels. If you connect this controller to a 12 volt battery bank, which is the most common, the maximum input voltage must not exceed 30 volts DC. When you use PWM controllers, you must use what are called so-called battery panels, that is panels with a maximum power voltage of 17.2 volts or similar. If you need to use more than one panel, they should be connected in parallel to increase the current rather than the voltage. So that is PWM controllers. They are usually cheaper than the PWM controllers and are ideally suited to smaller systems where cost is more of an issue. I shall now take you to the MPPT controller, and I shall tell you about this one. This controller has a maximum input voltage of 70 volts, so you can use higher voltage panels such as grid tied panels, which are meant for rooftop installation, and grid tie inverters. These panels are much higher voltage output than the so-called battery panels, so you can either use these panels or wire more than one battery panel in series. So this can handle up to 70 volts at a maximum current of 15 amps. So this controller can take the up to 70 volts input and convert it down to 13 to 14 volts and boost the current up to a maximum of 15 amps. This controller is a fairly cheap model. It was bought from eBay for about £30. The top of the controller is fairly bland. I have not actually seen a model number on this controller, so that is that. On the front it has an LED display, a LED numeric display, and this one can show you the wattage coming in from the panels, the current from the panels, the battery voltage, the load current, as this controller has a load output. It features a timer which can turn devices on and off after sundown, so for a night light system, for example. The only thing I do not like about this controller is the fact that the wires are hard wired to the controller, and for some reason come out of the front of the controller, which gets in the way when you want to read the numbers and makes mounting it very awkward. So I don't use this controller. So that is that. I shall take you to some other controllers to show you. So I will show you some other controllers. This is my Sunsaver MPPT charge controller. This controller has a maximum input voltage of 75 volts, so I can connect grid tie panels to this controller or several battery panels wired in series. This features the MPPT technology, so it can convert a high voltage from the panels to the voltage required to charge the batteries and make a gain on the current. You won't make any power gain because the voltage and the current are a fixed relationship, so if one goes up the other must go down, so the power stays the same, albeit for a little bit it is lost in the controller, but to all intents and purposes it is the same. This controller has some LEDs on the front to show the charging status and the charge of the battery. It has 3 lights here. The green light shows if the battery is fully charged. The middle light shows the battery has an intermediate level of charge, and if the red light comes on, your battery is dangerously low, and you should cut off all the loads and charge your battery at once, either with solar or with a mains battery charger. The light on the left flashes when the batteries are fully charged and the controller is in a maintenance float charging mode. This controller also features a connection for a remote meter, which also is the same. Also allows you to plug in an adapter to connect it to your PC for logging data, as this controller can record data over a period of time. I will show you what the remote meter looks like. This is the remote meter. It's currently showing me the voltage of the batteries. It has a LCD numeric display which shows the voltage of the battery, the charging current of the battery, which is 0.4 amps in this case. If I press the button here, that controller has a load output, and this is the current being drawn from the load output. It also has a temperature sensor, which it uses to vary the charge according to the temperature. And lastly, it gives you a numeric readout of the voltage from the solar panels. As you can see here, it's 34.66 volts, which exceeds the input voltage of the PWM controller I just showed you a moment ago. Okay, I shall go back over to the controller. I have another controller up here. This is another PWM controller, a 12 volt only controller, but this one can charge 2 separate battery banks. It's mainly used in RVs and motorhomes to charge the house battery for the living accommodation and the starter battery for the engine. It gives priority to the battery in the living accommodation, since it's used more than the battery that starts the engine, but it will keep the starter battery topped up as well, so that when you want to drive to another location you can actually start the vehicle. This controller is a bit more basic. It has a light at the top here which lights green when charging. If there is any malfunction, the light turns red, i.e. if the batteries fall too low or there is some problem with the controller. It has some dip switches on the front which allows you to set the battery type and the charging priority. This controller cost me £45 second hand, and it's used on a small system here. The main controller that I'm using over here was purchased brand new for approximately £200. So the key things with controllers is that when you wire your solar panels, you need to know which controller you're going to use, or which type of controller. Using PWM controllers, you wire your battery panels, the 17.2 volt panels, you wire them in parallel to give more current. And if you are using an MPPT controller, you can use high voltage grid tied panels or several battery panels wired in series to increase the voltage and minimize the current in your feed cable. So that is this part about charge controllers. I shall continue on in a moment on the next section of my videos. Okay, we are now in the next section of the video, and this section is about batteries. Now, it's all well and good generating your solar power during the daytime when the sun is out, and the solar is good. But normally we want to use our power when the sun has gone down in the evening and at night when the weather is raining and miserable, and basically usually want to use the solar power when the sun's not available. So we need somewhere to store the energy that we are generating. So for this you will require batteries. One battery or several batteries. So we will take a closer look at batteries. For most DIY solar power systems, you will be looking at using 12-volt batteries. Since there are many 12-volt devices on the market and 12-volt adapters, this would seem a sensible choice to go. So here we have some batteries. The most common type of battery used in solar power systems are lead-acid batteries. There are two main types of lead-acid batteries. They are the sealed gel type batteries, such as these ones, and the flooded type batteries, which you will be familiar with under the bonnet of your car. These batteries here contained the sulfuric acid in a gel, which means that if the battery is damaged in any way, i.e. if the casing becomes cracked, then no fluid will leak out and cause a mess and create a danger due to the corrosive aspect of the acid. The flooded type battery contains liquid battery acid which surrounds the lead plates, which you'll be familiar with this in your car, but your car has what is called a starting battery, which is designed to give a quick burst of energy to crank the engine and then be charged by the alternator as you drive your car. In this circumstances, the battery is not drained a lot unless you have any problem in starting the car, and then it will be charged all the time that you drive. So those sort of batteries are not suitable for solar power systems. The batteries shown here are valve regulated sealed lead acid batteries. These are AGM batteries, which stands for absorb glass mat. The acid is held in a spongy glass mat, but it is not 100% saturated. There is no loose fluid in the mat, so if the casing gets cracked or damaged, there is no fluid to leak out. Also, with the flooded batteries, they give off hydrogen gas when they are being charged, and that is very flammable and in circumstances can be explosive. So these valve regulated batteries, they recombine the gas inside the battery, so under normal conditions no gas is vented off, which is a good safety thing. These batteries can be mounted in any position. Some can even be installed upside down and nothing will leak out. You can obviously not do that with flooded type batteries. For solar power systems, you will need so-called deep cycle batteries, which means batteries that are designed to be regularly discharged down to a maximum of 50% discharge and charged back up again without suffering no ill effects. Car batteries must never have this done to them, otherwise they will fail in just a few months, and we don't want fumes and leaking acid in your house, so I do not recommend using these. The same applies to so-called caravan batteries and leisure batteries. These are not meant to be installed in an enclosed space like in your house, so do not use them. So with deep cycle batteries, you can discharge them down to 50% without no problem. In your solar system, you will probably use your system in one of two ways. I will just come down to this battery and show you. Your system will either be for standby use, i.e. it's charged constantly by your solar system and charge controller, but is only used in times of urgent need, i.e. during a blackout, or if you have a urgent need for power when none other is available. That would be for standby use. Or your system will be in a cyclic system where you charge the battery whenever the solar is available, and you use it either in the evening, at night, or when the sun is not available. Then this would be cyclic use, and that would be that. Now, batteries come in various capacities, that is, their ability to store electrical energy. This is measured in units called ampere hours and is written as capital AH. The amp hour rating is the ability of the battery to store energy. Generally speaking, the higher the rating, the bigger the battery, usually. They come in different ratings. I have two batteries here. This is the 18 amp hour battery. This is a common size battery that you might find in car jump starter units. This is a common size battery. Next to it there's a 6 amp hour battery. Some of these are rated at 7 amp hours. These are the so-called UPS batteries. They're used in computer uninterruptible power supplies, so your computer will still work for a short while during a power outage, so you can shut down and save your work. They are also used in alarm systems. Because they are very common sized battery, they are easy to get hold of and usually fairly cheap. As I said, these are sealed lead acid type batteries. The lead component of the battery means they are usually heavy, since lead is a heavy element. Also, batteries must be recycled at the end of their useful life, as lead is a toxic material, along with the sulfuric acid that is contained within them. So, one thing to note, as the batteries get bigger, weight can become an issue, either if you have to carry the batteries around, or the structure that you mount them on or in must be able to bear the weight of the batteries. Batteries must be charged with care and attention. You must not overcharge batteries with too high a current. Usually the bigger the battery, the higher charge currents it can cope with. This is an 18 amp hour battery, and this one is quite rare as it has the charging information printed on it. You can see here that if we're using it for standby use, we should charge it to a value of 13.5 to 13.8 volts, and the charging current must not exceed 3 amps. If we're using it for regular discharging, which is cyclic usage, then your controller should charge the battery to 14.1 to 14.4 volts, and again not exceed 3 amps. Also, batteries must not be installed in hot places, and the biggest thing that must be avoided is a short between the two battery terminals. This will usually result in big sparks, the wire getting very hot, the insulation melting, the battery might get very hot, and in some very rare cases may even explode. So short circuits are to be avoided at all costs. Also, batteries have different terminations. This is the method of which you attach your wire to the battery. This one here has a bolt hole where you can attach a ring terminal with a nut and a bolt. So that is one type of terminal. This other battery here has a different kind of termination. It uses spade terminals, which just push onto the terminals. and that is that. For indoor use, I would recommend you use these valve regulated AGM batteries. If you're buying larger batteries, these can be expensive. A cheaper option may be to use flooded deep cycle batteries, which have fluid in like your car battery, but these need to be installed outside or in an enclosure which will vent off the gas produced from charging. We are doing a DIY system, so we would normally use 12 volt batteries, but there comes to a limit to the size of 12 volt batteries that you can buy. At that point it might be easier to buy two 6 volt batteries and wire those in series, since they make larger capacity 6 volt batteries. And if that is not big enough, you can buy individual 2 volt batteries and wire those in series to get 12 volts. Lead acid batteries are actually made of 6 individual battery cells. Each cell produces roughly 2 volts, so in a 12 volt battery there are 6 cells wired in series, as you can see here. These are the vent caps for the cells in this valve regulated battery. Should anything go wrong and you overcharge the battery, these vents will vent out any excess gas to prevent the battery from exploding, although all care should be taken to avoid this. So this is the section about batteries. There are other types of battery on the market, such as lithium-ion batteries, but these are A, very expensive, and B, they are not compatible with normal charge controllers. Your charge controller will have various settings for different types of battery, usually along the lines of gel, AGM or flooded batteries, as the flooded batteries need a higher voltage than the gel or AGM batteries. You need to make sure that you select the right setting. So that is the end of this section. I will see you in the next section. Thank you. Okay, so now you have your batteries and your solar panels and your charge controller. You're thinking, well, what can I run on a 12 volt solar power system? Well, the answer to it is that many things can be run from your 12 volt solar system. The loads that you run from your system will fall into 2 main categories. There will be DC loads that run directly from your batteries, and there will be AC loads which will require the use of a power inverter, the things that you would normally plug into your wall sockets in your home, but we'll come to that a bit later. So I will start with the DC loads, because these do not require the use of the inverter and make more efficient use of your batteries. They will run down more slowly than if you are running a power inverter. So let's look at the range of things that you can run on your 12 volt solar power system. On my workbench here I have a selection of devices that I will cover in a little more detail. Okay, so with 12 volt devices, they can either be 12 volt devices which run directly off of 12 volts, so things that you would use in your car, for example, things that come with a 12 volt cigarette lighter plug that you would normally plug into the lighter socket in your car. So I have a few devices like that here. I have a 12 volt bulb. This is a compact fluorescent bulb, a special DC bulb, unlike the ones that you fix into the light sockets on your ceiling at home. So this is a 12 volt bulb. It says clearly here on the packaging 12 volts. I bought this from a company called On Solar, who make a range of 12 volt light bulbs. They make them in different fittings. This bulb is actually a bayonet one. So it says here on the box, high quality 12 volt DC compact fluorescent lamp. So this is a compact fluorescent lamp. It has a power consumption of 20 watts at 12 volts DC. It has a colour temperature of 4200 Kelvin, which is a medium white, and the typical life of this bulb would be 10,000 hours. There is a warning on the box that you must not accidentally plug this into a 240 volt AC lamp socket, because it will get instantly destroyed. So, word of caution there. Okay, and you can see that this is rated A for efficiency, so that is good for our battery life, because it is very bright with a low power consumption. It says on the box here that, as a guide, it produces 1200 lumens. I will plug mine in and you can gauge for yourself. My workbench is wired for 12 volt devices. I have a 12 volt socket on my workbench, so let's plug it in and see how it goes. Okay, just going to plug it in the plug. Okay, and there we go. You can see the bulb is very bright. Obviously you would mount your lamp socket on a wall or ceiling, or you could convert a ordinary table lamp by cutting off the plug and fitting a 12 volt plug. Just a note of interest here. With a bayonet light fitting, there are obviously 2 pins in the lamp socket, and these bulbs are polarized, i.e. they will only work one way round, so don't be worried if you pop it in your lamp socket and it doesn't light up. You have not broken it. Simply take it out of the lamp socket and twist it 180 degrees and pop it back in, and you should find it should work fine. These bulbs are protected against reverse polarity, so putting them in backwards in the lamp socket should cause no long-term harm. So that is a 12 volt compact fluorescent lamp. I will just unplug it now. Also, you can buy 12 volt voltage adapters. I have one here. It plugs into the 12 volt cigarette lighter outlet. You can see here that the voltage output is adjustable, so you can power devices that need less than 12 volts. So you can have 9 volts, 6 volts, 5 volts, 4.5 volts, 3 volts, or just 1.5 volts. And this converter can output a maximum of 1 amp, so you can run any device with a consumption of up to 1 amp. So this would normally be used in your car to run things like handheld games, charge phones, satellite navigation systems, cameras. The list is endless really, but you can use this at home. I had this connected to a set of amplified portable speakers. The socket on the back of the speakers says that it needs 10 volts DC at 900 milliamps. I have tested it on the 9 volt setting, and they run fine with no problems. So that's one thing you can have. You can have, I can run my soldering iron. This is a 12 volt soldering iron. this is actually meant to be used in your car to make repairs in your car, but I find it works fine on my workbench, and I use it for soldering. I just plug it into the socket on the back of my desk, which is very convenient. Some other devices that you can use, I have this small stereo amplifier, and I can plug my speakers into it. It's, despite what it says 500 watts, it's not a 500 watt amplifier. It may run a couple of watts maybe, because the big giveaway is on the back of the unit. You can see here, I have the leads for it, but it says here that the power consumption is 12 volts at 0.5 amps. Well, if you do some maths with that, that only comes to 6 watts. So, but 6 watts is ample when used indoors. The music can be loud, so that's one thing I've used before. It has some connections on the front where you connect your cables and the volume control. It also has a handy USB socket to charge your MP3 player, but please note it will not charge iPods. I have tried and it doesn't work. So that's one use, a 12 volts sound system. Okay, we have here we have a 12 volt light, LED light. This one is hardwired to my bench. Also at the back, if I tilt the camera, there is a fluorescent light, a 12 volt one. This one came from a caravan. You would hardwire it into the wiring of your caravan. So that is a fluorescent lamp. That is a 13 watt lamp, and the whole unit consumes about 14 watts, so that's relatively energy efficient. The main thing if you're using lighting on 12 volts is, let's make some space. Okay, this is a 12 volt filament bulb. This would be from the reversing light, or reversing light from a car. These type of bulbs, this is a 21 watt bulb. These are not recommended for use with solar power systems, because filament bulbs consume a lot of electricity for the amount of light they give out. They also get very hot, so these are not recommended. These are best used in your car, but not for your solar system. The other main DC usage you'll have is for 5 volt devices. Basically anything that's USB, which you plug into your computer, is fair game as well. To use these on your 12 volt system, you would simply buy a USB charger adapter. I have one here. It's a single outlet model. Okay, this one puts out half an amp at 5 volts. So, and you just plug that into your socket, and the light comes on, as you can see there. You can also buy more powerful models. I have one here. This one has a 1 amp outlet and a 2 amp outlet. The 2 amp outlet is required for things like iPads, because they require a higher current. If you plug them into the 1 amp or 500 milliamp outlets, they won't charge, and again that just plugs into the socket as well. I have actually installed a dedicated USB charging device. This one is wired directly to my 12 volt electrics, so it doesn't use the other outlet I have, so it is free for things that use a cigarette plug. Okay, so the 12 volt USB charger can charge MP3 players and phones and iPods, your sat nav, phones, and a list of devices that grows longer every day. Other 12 volt devices you can have is DC fans. This is a 12 volt fan from a computer and it's rated at 12 volts 0.24 amps. Again, these fans come in different sizes. I also have a USB fan that plugs into the USB charger. I shall turn it on. And you can see it working. You can probably hear it working as well. It can be used on the desk to cool for cooling, or to blow away fumes when I'm using the soldering iron. So there's that. The 12 volt list of devices is very large. You can buy anything that is made for the caravan market or in-car market, so there are lots of devices available for that now. Okay, I have a 12 volt fan here. This is a bigger fan, and so that's the DC side of things. If you want to run AC devices, then you will need a power inverter. This is my power inverter. It's the 300 watt pure sine wave inverter. Inverters fall into two categories: pure sine wave and modified sine wave. If you're going to run anything electronic, I recommend you use the pure sine wave. They are more expensive, but they are more compatible with devices you might want to run. A word of warning about inverters: you should treat the output from your inverter exactly as the same as from the wall sockets in your house. The electricity produced by them is just as dangerous and will kill you if handled without care. So that's that. I have an ammeter on my setup so that I can see how much current I'm drawing from the battery bank. That can be useful to know. I also have a modified sine wave inverter. I have one here. This is a Nikkei. This is a 600 watt inverter, though for short periods it can withstand a surge of up to 1500 watts for a couple of seconds if something needs to start up. Note here that the cables that come with it are quite thick, because I think, if my memory serves me right, this inverter draws 80 amps to produce 600 watts. Ideally, when wiring your inverter, you want to wire the cables directly to the batteries to avoid the use of crocodile clips, because that's not a good way to connect inverters to your battery. When connecting your inverter to your battery, you must use an inline fuse, a suitably rated fuse, and the cable should be thick enough. It is a good idea to have some kind of isolating switch, so that if you need to quickly isolate your inverter, you can. I have one on my main system down here. This switch here cuts off the inverter and everything from the batteries. You need to make sure that all your wiring is of adequate thickness to prevent overheating and a risk of fire. This is my DC panel. It's my distribution board. When wiring all your circuits to your batteries, you must have a fuse. So there's fuses here and switches for isolating if need be. With my AC inverter, I only run low power devices, it is rated at 300 watts, but I rarely exceed 100 watts. With the inverter I run battery chargers to power all my battery devices, lights and other equipment. So these are the plug-in type chargers. I have another charger here which you might be able to see, and you can plug in the adapters for all your various devices. This is a radio which charges from the mains or solar. I mostly charge it from the inverter, since in a way it is solar powered, so that's useful. Okay, there's a fan. This is a car fan. It comes with a cigarette lighter plug, and that is that, for the load type of things. Obviously, when you are using an inverter, I shall come over here, the main thing with using inverters is that you should understand that you are not going to run large appliances on your DIY solar system. So things like washing machines and vacuum cleaners are an absolute no-no, since these devices can consume over 1,000 watts. If you do some maths, 1,000 watts at 12 volts soon comes to a few 100 plus amps, and that will run your batteries out very quickly. So it's best to stick to small devices, low power devices, when using your inverter. I shall come to, right, this is my main system. It is a fixed system because it is not movable, but you can have smaller systems which are portable. This is a small system that I have on my windowsill. It's basically a wooden box that I made with a 55 amp hour sealed gel type battery, so it doesn't vent off any gases under normal conditions. It has a battery voltmeter on the front, so you can keep an eye on the charge. There is a switch and a 12 volt DC outlet. At the moment it has a USB charger plugged into it. The switch simply cuts off the battery from the 12 volt outlet. This system has a fuse between the battery and the outlet, which is what I said in earlier videos. If I draw more than 5 amps through this fuse and the outlet, I will simply blow the fuse, so that stops any overloads. This system has the charge controller mounted up here, although if I was, basically because I'm charging my power box and some spare batteries that are being maintained, if I was only using just the one battery, I could mount the charge controller in the power box and have the solar panel on a long cable and simply just plug it in to the charge controller via a socket on the side of the box. I just have it set up this way because I find it convenient. But if you could use this box, i.e. when you went camping, then you would have the charge controller inside the box and the solar panel would be on a long cable that you would just plug into a port on the front. I have done this in the past, that's why there's a hole labelled solar here, because there used to be a socket there. So you could use this to run phone chargers and lights and small things like this. With a system of this size, I would not recommend using an inverter of any kind, because it would flatten your battery quite quickly. The thing to note when using your charge controller is that you must connect the charge controller to the battery first, so that it can automatically, most charge controllers auto select the battery voltage. So in order for them to do this, you must hook them up to the battery first. Wait a couple of minutes for them to make the right selection before connecting the solar panels. If you do this in the wrong order, then your charge controller might not work properly. So always follow the instructions that come with your charge controller. I will see you again in the next section of my video series. Okay, we are on to the next section. This section is going to be about meters and gauges. When you have your solar power system, you will need to know certain parameters such as the voltage of your batteries, the current being produced by the solar panels, your load usage, the power generated, and data like this. So meters and gauges are your instruments to see how your system is working, and if anything is going wrong, these will alert you to them. Okay, this is the evening, so it's a bit dark, so I'll see how I can do. Okay, this is my power box, and this is the battery voltage gauge. This tells me the charge of the battery. So you can see here that the charge is well in the green area. In fact, it's past the 100% mark, so that is good. You can see that the dial on this meter is calibrated into different sections. During normal use, you would like the needle to stay in the green area. That's between 12.2 and 14.67. Okay, so anything above 12.8 is in the charging zone. So in the daytime, when the sun is striking the solar panel, if the needle is in the green charging area, then you know that everything is connected correctly and that your battery is being charged by the solar panel. In the evening, when the sun is not shining, the meter shows you how much charge is left in the battery. So as I said, you want like the needle to stay in the green area, so you would try and keep the voltage above 12.2 volts, which is 50% capacity shown on the meter. It's a bit hard to see here because it is dark. You can go occasionally into the yellow area, but I would advise you not to, and you definitely do not want to go into the red area, which is below 11.2 volts, because that means your battery is seriously depleted and you should stop using any load immediately and try to find some way to recharge your battery. So that is the voltmeter on the portable system. I will take you over to the main system, where I have some more elaborate gauges on this system. Okay, I will try my best to show you. Okay, this is the meter on the solar panel input. As you can see, the label says under the meter. This gauge shows everything to do with solar generation. In other words, power being generated from the solar panels. Okay, this screen scrolls through different things, so I'll try to keep up with it. Okay, in the top left corner is the amp measurement from the solar panel. Obviously now it's at night, this reads 0. So, those big surprises there. The value to that was the number in the top left. The number in the top right is the voltage coming from the solar panels. You can see now it says 9.68 because it's at night. Usually in the daytime this could be in the mid to high 30s or even up to the low 40s. I will just come out a bit. Okay, just mind my finger. Okay, let's go back in again. Okay. Let me just come up again. This is a bit of a strain for me. Okay, the figure in the bottom right is the power coming from the solar panels. Obviously at night this value reads 0. So now we'll turn our attention to the number on the bottom left as it scrolls through different things. Okay, I will just tell you what it says. Okay, we have peak power from the solar panels, which is I'll just wait for it to come around again. We have 72 watts. The next number is the number of amp hours generated, the number of watt hours generated, the peak current from the solar panels, the minimum voltage from the solar panels, and then it goes round and round again. So I'll just come back a minute just to rest my hand. So we obviously have the peak wattage, that's the highest value generated. Then we have the peak current. Obviously if this value reads 0, that means there is a break in the connection between the solar panels and the meter. It would also show 0 current, 0 watts, and you would have 0 volts coming in. So this gauge would alert you to that if there was anything wrong. This meter shows the number of watt hours generated. This has to exceed your usage, otherwise your batteries will end up running down. And the number of amp hours is another generated figure, the capacity being generated. So obviously the watt hours are the same. The watt hours is what matters because you use your load in watt hours, so the generation must be greater than the number of watt hours used by your load, otherwise you will gradually deplete your battery down to nothing and it will get sulfated and you won't be able to charge it again. If I come to the meter on the bottom, the light is a bit glary on this meter. Okay, so this is all to do with the DC loads. Everything here apart from the inverter, as the label under the meter clearly states. You can see that I'm drawing 1.64 amps from the batteries, so that's what my load is consuming. The number on the top right is the current battery voltage. It is 12.62 volts, so that's okay. And if we come to the bottom right number, that is the amount of watts I am using from the batteries. This is everything apart from the inverter. And then as we scroll on to the left, we have used 113.7 watt hours. So that's less than what was generated, so I'm actually gaining. And my peak current drawn was 1.79 amps. My peak wattage was 22 watts, so that's all okay. So using this as your load meter and you compare it with the product of what you're generating, you can see what the difference is. If the production is less than the generation, then you need more solar panels, you need to reduce your load, or you need more batteries. So that's what your gauges are there to show you. I have a table here to do with state of charge of the battery, and my battery is at 12.6, so they're 100% charged. I also have a gauge on the inverter I showed you earlier. I am running my laptop computer at the moment. You can see that the meter is hovering around, but it says just under 5 amps, so that's okay. So that's the power being drawn by my inverter. I'm using my inverter to power my laptop computer. I'll show you that in a second. I also have a kilowatt meter that records the amount of AC usage. I'll just shine a light so you can see. At the moment we are using approximately 30 watts. That's the current drawn by the laptop computer. This can jump up to 100 watts depending on what the computer is doing. So all these gauges and meters allow you to see how your system is working, and if your system is sized correctly, and also your meters can warn you of anything that is wrong with your system. If you're not generating enough power for the amount you're using, then you'll know that you need either more solar panels or batteries to use less load, or to use your load for shorter periods. I will just show you now that I am running the laptop computer. If you follow the cable, you will see that it goes down, down, down to the inverter battery system. It is not plugged into the wall because the wall socket is down there and there's nothing plugged into it. This is the grid powered socket in this room, and I can say gladly I don't use it very much I don't use it much at all. If I have not used this plug socket in several months. All my power is coming from my battery system. So as you can see, I'm running the laptop. I am running the 12 volt CFL bulb I showed you earlier to make this video. I am running the LED light above the workbench, and the only other thing being used, that is the only mains powered light, and I could do easily without it if I was not making this video. So that's what I do. During the day, in the evening, I charge my devices. I am charging my iPad over here from a USB charger, the 2 amp one, that is connected to a cigarette lighter socket. At night I would be charging the iPod. The cable ends here. The only reason I'm not charging the iPod is because I'm using it to make my videos. Yep, I am making my videos on my iPod Touch, which is solar charged. It's charged from the 12 volt battery bank, but that ultimately gets its power from the sun. So everything here is ultimately solar powered. It's battery powered, but the batteries are charged from the sun. So in the end, that's where the power comes from. It's a battery derived solar charged power system. So that is this section. Until the next section, I will see you later. Just while I think about it, I did forget to show you the remote meter that is connected to the charge controller. So I'm just going to show you this quickly as well. We just turn on another light, and I'm going to sit on the bed and show you this meter. Okay, this is the current battery voltage with me running the laptop computer and the lights. The batteries are at 12.65 volts, so according to my table that means the batteries are fully charged still. If I press some more buttons, you can see that the amps coming from the solar panel is 0, since this is the night time. But if it said this in the daytime, then I know that the connection between the solar panels and the battery is broken and it needs attention. This meter also shows the minimum voltage that your batteries ran down to, which is 12.53. As this meter records this over a long period of time, you can find out if, say, overnight your batteries fell to a dangerous level by flicking through on this meter. So 12.5 is okay. Then this is the meter shows you the highest voltage the battery has reached during the daytime. So here it says 14.35. So this means that everything is working correctly and the batteries are getting a good charge. If this number is too low, you either know that the weather was bad or that your solar panels were being shaded by something, or that you just need more solar panels to charge your batteries. So that's that. If I go to a different menu, this meter then tells you the amount of DC load that you are drawing from the charge controller and ultimately the batteries. I'm drawing 1.8 amps, but this figure excludes the inverter, since the inverter is wired directly to the batteries and not through the charge controller. It does not know the amount being drawn by the inverter. So this is the room temperature by the charge controller. It's 24 degrees Celsius. It's not as warm as it was in the daytime, but it is still fairly warm. And the current voltage from the solar panels is 3.12 volts. Obviously this is the very late evening, so that's low. But if you had readings like this in the daytime, that means you have a serious problem with your charging system. There is something wrong with the solar panels, and that would need your attention. And then we go back to the batteries. This meter has a green status LED. It's up here. In the daytime, that will light up green to indicate charging. If for any reason in the daytime the indicator is not on, then you know that you have a problem. At the bottom here, there is a battery indicator. The green one shows the battery is fully charged. There's the yellow one in the middle, shows an intermediate charge, and the red one on the far right shows you that your battery is dangerously low and you need to go and fix a problem very quickly. Normally this battery voltage at night would be higher than this. It's at this value because I'm using the inverter to power the computer and all the other lights that I'm using to make this video. So this is artificially low for what it would normally be. But as far as batteries go, this is fine. Any value above 12 volts is considered okay, because 12 volts would be 50% charge. I've never been down that far before. The lowest value I've ever seen was 12.4, and that only occurred once, so I not have any problem here. My batteries seem to be enough for what I'm using, so that was just a quick extra, as I just forgot to mention it in the section that's just gone. So until next section, I'll see you later. Okay, in this section I am going to talk about battery chargers. I mentioned earlier in other parts of the video that if your battery is ran down until the low battery light comes on your charge controller, your battery is seriously considered to be flat. At this point, it is a wise idea to charge your battery immediately so that it will be charged up and it won't be left standing in a discharge condition getting sulfated up. If this happens, your battery will be hard or nigh impossible to recharge. If you have large capacity deep cycle batteries, this will be very expensive and you won't want to do this. So, if your battery is run down due to some system malfunction, you using your loads too long, or the solar panel becoming disconnected from the charge controller accidentally, then now is the time to charge your battery. The other time you might need to use a battery charger is during the winter. During the winter months the sun doesn't shine much, and when it does it's not very strong, so you won't get much charging. So the only solution to this is either to cut back heavily on the loads you're using, use them for much shorter periods, or top your batteries off using a battery charger. I had to do this during the last winter as the weather was miserable, it rained for weeks on end, and my solar generation was only 2 or 3 amp hours per day. So I used a battery charger. There are 2 main types of battery charger available on the market. They are all powered from the mains. There are car battery chargers, the very simple ones that you just charge your car battery with, and there are special battery chargers meant for deep cycle batteries and leisure batteries. These are automatic smart chargers, and this is what you want for charging your battery. These battery chargers can detect when your battery is getting full and switch to a maintenance charge to stop your battery from getting overcharged. Overcharging your battery is almost as bad as undercharging your battery. With the sealed type batteries that I recommend you to use, if you overcharge them for long periods of time, they will vent out gases from inside the battery, but since you can't add more water to replace the gases lost during overcharging, your battery will die earlier than expected. So overcharging is just as bad as undercharging, and in some circumstances can be dangerous. If you pass excessive current into your battery, it may overheat, vent, or in rare cases explode. So let's have a look at some battery chargers. I have 2 battery chargers here. One is for small capacity batteries and the other for larger capacity batteries. Let's have a look. Okay, the first charger I have here is a SunPower. It's a dedicated sealed lead acid battery charger. As you can see on the front, there are a row of indicator LEDs. This charger can charge 4 different voltages of batteries from 2 volts, 6 volts, 12 volts and 24 volts. The charger automatically determines the correct voltage when you connect it to your battery, so that's useful, although occasionally that can be problematic. It also has a red charge indicator which lights up when your battery is charging. The indicator light gets dimmer as your battery charges up because it is drawing less current, so when you first connect the battery this light should light up brightly. If you connect your battery to this charger and the red LED does not come on, or the 24 volt light comes on, even though you have a 12 volt battery or a 6 volt battery, This tells you that there is something wrong with your battery. It's usually because you left it discharged too long and it has become sulfated, and this kind of battery is very hard or impossible to recharge. So this condition is best avoided at all costs. Now this is a small battery charger. It would be suitable for the 6 or 7 amp hour battery I showed in an earlier part of the video, or even the 18 amp hour battery. But if you used it on a large battery, such as the 100 amp hour batteries I have in my main bank, this will take a very long time, and the charger will get hot, which will not do it any good. If I just turn the charger around, you can have a look at some numbers on the back of the charger. Okay, you can see it has a model number and it is a lead acid charger. It plugs into the mains and draws approximately 17 watts. As you can see, for the different voltages of batteries there is a maximum output current. So if you are charging 2 volt batteries, you can put out 900 milliamps. If you're charging 6 volt batteries, it can put out 700 milliamps. For 12 volt batteries, you can put out 600 milliamps. And for 24 volt batteries, you can put out 300 milliamps. You'll see here that this current is not particularly high, and if you had a large capacity battery, the amp hour rating of the battery divided by this charging current will equal many hours, and it will take a long time to get a charge. Also, this battery charger has crocodile clips on the output leads, although if your battery uses a different kind of connector, it would probably be easier to change the connector for a suitable one for your battery. At one time I had the spade terminals on this charger, as I was using it on those type of batteries, and getting crocodile clips to stay on a spade terminal battery is very difficult, and it was easy to short out the battery, so I changed them for spade terminals. At a later date I changed it to crocodile clips because I was using it on a different battery. So that is the small battery that's suitable for the alarm system type batteries or the UPS batteries, and the 18 amp hour batteries that you typically find in car jump starter units. So I will move on to the larger battery charger now. This is a Challenge fully automatic battery charger. It is a 12 volt only battery charger, so you can only charge 12 volt batteries with this charger, but it can push out 11 amps, so it is more suitable for larger batteries. That's 11 amps maximum. On the front it has some indicator lights. There is a light that indicates that your battery is fully charged, a light to indicate the battery is charging, there's an indicator light to warn you if you connected the battery the wrong way around, and there is a battery voltage indicator, a very simple one. If the red light comes on if the red 20% light comes on when you connect the battery to the charger, your battery does need charging. If the 80% green light comes on when you connect the battery to the charger, then your battery is pretty well charged and your solar system should be able to handle topping it off. Okay, underneath the battery indicator there are 2 switches. Now this charger can be used with different types of 12 volt lead acid battery. It has a position for standard car type batteries, such as you find under the bonnet of your car. It has a position for sealed and gel AGM type batteries. This setting will use a lower voltage than the standard setting, which is meant for the batteries with the liquid inside. with the battery fluid inside, the type that you use in your car. Underneath there is another switch. This switch is used to change the charge rate, on the basis that if you are charging a car type or car size battery, you will need a higher current than if you are charging a smaller battery, like the ones found on mopeds and motorbikes. This can be used for smaller batteries, so that would use a lower charge current. As I said earlier, you do not want to use too high a charge current for the size of your batteries. For the batteries in my main bank, the 100 amp hour batteries, I would use the car setting with the other switch set to sealed and gel type batteries. As they are 100 amp hour batteries in my main bank, and this charger is suitable for batteries up to 110 amp hours. The bike setting is suitable for batteries up to approximately 20 amp hours. If I use this charger on my main bank, bear in mind I have a bank of 3 100 amp hour batteries, this charger will charge them up in a couple of hours, so I don't have a problem. This charger is rated up to 110 amp hour batteries. Basically, if you have a much bigger battery, it will take longer to charge up. That is the only thing. This charger also has a 20 amp fuse in the output, so if there was a malfunction it would blow the fuse. It also has a light to show if the fuse is blown. If the fuse is blown, the light simply won't come on. This charger is also reverse polarity protected, so if you hooked up the clips the wrong way round, a warning light will come on, but the charger won't output any current. This charger will not output any current until you actually connect it to a working battery. This is to avoid accidental short circuits of the crocodile clips on the output. It's a safety thing. These battery chargers are meant to be used indoors, just so they don't come into contact with any moisture. You should always connect the batteries to the charger before plugging in the charger. This is also a safety thing, so you won't get a spark when you connect the clip to the battery. So that is battery chargers. This also has an overheating protection. If you connect it to a very flat battery, it will draw a large current and the charger will get hot. So if this happens, it will simply switch off and it will cool down rather than overheat and catch fire maybe. So battery chargers are an essential part of your system, because there are times when the sun doesn't shine, i.e. in the winter, during stormy conditions, and with our typical British weather, this could happen at any time of the year, but mainly in the winter. Also, with your system, you need to do maintenance. The maintenance can be quite simple, just to go around your charge controller and look at the indicator lights. You may be wondering why I have covered the indicator lights. The reason for this is that this is in my bedroom, and at night the LEDs shine brightly and keep me awake, so I covered them up. So during your normal maintenance, you'll look at the lights on the charge controller and check that you have in my case, a green light on this controller shows that it is charging. I'm doing this in the early afternoons and the sun has been good. It is reasonably bright. The full battery indicator is showing on the charge controller, so I know that everything is okay. I'm just going to cover the lights back up again. As I told you before, you should keep an eye on all your panels and gauges. You can see here that I am putting in 60 watts, so everything is good. The voltage from the solar panels is 34.5 volts, so that's good. I'm putting in 1.73 amps at the moment. I peaked earlier. The peak solar panel power was 126.8 watts, so that's good, and the batteries are getting a strong charge. My current peaked at 4.22 amps from the solar panels, so I have a good connection there. Now this is early afternoon and I'm already up to 10.5 amp hours, that's 359 watt hours, and the power is fluctuating around at the moment, but it's approximately 55 watts, so that's okay. So by looking at my gauges I can tell everything's working fine. I'm typically using my system as I would. I'm running some battery chargers, and I charge my cordless power drill with the tool charger, which is plugged into my AC inverter. You can see we're not drawing much current at the moment because the batteries are all charged up. The kilowatt meter is showing a draw of 16 watts, so that's okay. On the power box, the meter's showing 14 volts, which is well into the charging area, so everything's working properly on this system, and the green light is blinking on the charge controller to show battery is full. If I just show you that the current on here is 1.5 amps approximately. I take you to the meter of the charge controller. It's an MPPT charge controller, so I have 1.5 amps on the solar panels, but 3.77 amps on the controller. I'll just push some buttons on the controller. Last night I used my batteries a lot and I went down to 12.42 volts. I ran the laptop until the early hours of the morning through the inverter. Today the charge controller has reached 14.31 volts. That is the high voltage cutoff. It then switches to the maintenance charge, so I've got a full charge today. The DC loads I'm using at the moment is 1.41 amps, so no problems with that. Today is a bit cooler, it's only 23 degrees Celsius, and the solar panel voltage is 34.13, so I have a good connection to the solar panels. Also, I shall come back to the workbench. Just push things out of the way a moment. I'm going to show you something with my system. I don't know if you can see it too well. Up here. Okay, I'm just going to rest my hands here. Bring the light in so you can see. Right, this is a rough plan of my solar panel system, the main system. You can see here that it's divided into three main sections. There is the battery box with the inverter on the front, so that was one part of the system. Then there's a section labelled charge control board, and another section labelled 12 volt distribution panel. These used to be two separate boards, but I then mounted them one above the other, so they are in one place now. So if we zoom into the battery box section, you can see that we have a connection to the battery bank at the bottom. Then there's the main isolating switch. There's followed by a fuse. It says 30 amps here, but I used a 25 amp fuse. Then there is a branch off that goes to the inverter through the ammeter, and then from the inverter to the AC socket, which is also on the front of the battery box. If we go back to the main fuse, we lead on from there through a 10 amp fuse, and then that wire goes to the control panel you saw beside my batteries. So if I zoom in on the charge control board, we start at the top with a connection from the feed cable. That's the feed cable from outside where the solar panels are located. So the wire comes in, goes through a solar isolating switch, basically a switch just to disconnect the solar panels if I'm working on the system. Then goes through a fuse. I actually have the switch and the fuse combined together, and it actually has a 13 amp fuse in it. I have not changed it as yet. From the 10 amp, from the isolating switch fuse unit, it goes to the solar panel input meter. That's my meter that shows the watts, amps, power, amp hours, etc. From there we go to the solar panel input of the charge controller. Then from the charge controller we have a lead that goes to the battery bank through a disconnect. This cuts the charge controller off from the battery bank, and that feeds down to the 10 amp fuse from the battery box. So there is a 10 amp fuse in the circuit to the charge controller. You will have heard before that I am using a 15 amp charge controller and wondered why I have a 10 amp fuse. Well, I haven't used a 15 amp fuse yet. I haven't got around to changing it, but I've not had a problem. From the charge controller there is a load output, and it goes from the load output to the 12 volt distribution panel, which in my case is below the charge control board. We go through a meter which records all the load usage. You have seen me show it to you before. There is then a load isolator. You may wonder why the load isolator is after the meter. The simple fact for this is that the meter is powered from the batteries through the load output. If I turn the load off for any reason, it would have reset the meter if it was on the other side. That's why it's here. So we have a load isolator, and then from the load isolator we go through the fuses. In this diagram the switches are above the fuse box, but when I actually built it the switches were underneath the fuse box, so they were reversed, but it's the same thing. And then from the switches underneath the fuses it goes to all the loads. So that is a diagram of my system. So it is useful to have a plan to show you how your system is put together. You can elaborate on the plan later, but that's just the way I planned mine out. I had components on 3 separate boards originally. Each board had a particular function. So I had the battery box section where the inverter was wired. You want to wire your inverter to the battery with the least amount of cable possible, so that's why it is actually connected to the battery on the battery box. I had one board that dealt with all the charge controlling and the solar input, and I had a separate board which dealt with all the loads, fuses, switches, and was a distribution panel. So that's how I planned my system there. Also, once you've got your system up and running, it is a good idea. You just move some stuff around. Okay. Let's just put it up here, it'll be easier to see. I keep records of what my meters say. This sheet is to do with all the power I generate all the time. I read to figures every day at the end of the day, so I can see over the year how my solar power generation is going. I have sheets going back to last year. If I just zoom in on a particular day, I will choose this day as also a particularly good day. This was the 8th of June. I make 4 measurements every day. I record the peak wattage, the peak amperage from the solar panel, the number of watt hours generated, and the number of amp hours generated. I only keep figures for the generation, but you may want to do figures for the generation and usage, and that would tell you how well your system is coping with your demands. If you always found that the generation was less than the load you was using, then you need more panels or more batteries, or you need to economize on the loads you're using. Hopefully, if you did this, you would find that your generation was more than your loads. I know in my case that it is, even though I don't record the amount of load usage. My batteries always stay up, so that means that that is true. I will admit that on certain days that the numbers look artificially high compared to other days. You'll usually find that the days on my chart with the highest figures are usually Sundays or Tuesdays. These are the days when I'm not at work and I use power in the daytime as well. You'll see on this particular day that the panels peaked at 150 watts. I had a peak current of 4.39 amps from the solar panels. From the charge controller, that would be in excess of 10 amps going into the batteries, and I produced 553.5 watt hours. These figures look artificially high because on these days I run the inverter all day, so some of this power is being used directly to power the inverter rather than charge the batteries. Also, the batteries will only draw the power required to charge them, so if they are fully charged, like during the weekdays when I'm at work all day long, I would be using no power in the daytime and all the charge would be going into the battery bank. Because I don't use the loads in the daytime when I'm at work, the batteries are usually well topped off and only need to draw a small current to be topped off. So if your figures look very low but your battery voltage is good, that would be the reason why. So I have sheets that I made for the whole month. At the end of the month I add up all the watt hours and all the amp hours for a monthly total, and then divide by 31 for an average, a daily average, and then compare back to the figures to see how well that matches up. I will grab a record from a previous month and show you. Okay. Do this very well. Okay, this was December 2013, the pretty miserable looking month. At the end of this month I produced 2,915 watt hours and 91.37 watt hours. So dividing that by 31 gave a daily average of 94 watt hours per day and 2.94 amp hours. So with the 90 odd watt hours per day, you will see that some were below and some were over. That was December. January's figures are 3,968 watt hours for the month and 128 per day, so there was a jump there. a similar figure with the amp hours. We come to February, we do 5,395 watt hours, which now pushes the daily average up to 192.7, so a big jump there, similar jump with the amp hours. I will now skip to April this year. Now we produced 8,707 watt hours in April. That made the daily average 290.2. Obviously there's more sun in April than there was in December and January. We produced 243.7 watt amp hours, and that pushed the daily amount up to 8.12. From April to May, the amount only went up by a small amount. We're on 8,984 watt hours for the month, 289.8 for the daily average. We was up to an average of 8 amp hours per day, so that's what records can tell you. Also, as well as looking at your gauges, the solar panels outside. When you put solar panels outside, they get covered in dust and grime and whatever's in the air, so every so often you'll need to go outside and clean your solar panels. I simply use ordinary window cleaner and a sponge. I happen to have the panels on top of my shed, so it's easy access with a ladder. Dirty panels will obviously produce less output, and that will lead to problems charging the batteries. If you look at your gauges and you notice that your charging is not as good as it was, and the weather has been good, that may indicate your panels need cleaning. So that is this part of my video. I will think of any other miscellaneous things I can think of, and that will come in the next section. So till the next section, thank you for watching. I will see you later.